which is dedicated to failure modes in electric machines, something like safe state, failure reaction, uncontrolled operation of an electric machine, and how to simulate and investigate about those things with JMAC. At first, let me say a few words to my former company. IV is an engineering service supplier, and we are basically servicing the entire automotive industry. So not only targeting to electric motors, but also doing any kind of component development or system development up to entire car derivation developments, which can cover several hundred people in the automotive industry. I'm responsible for electric motor design, and some are also power electronics and control. And we are basically designing electric motors from very small stepper motors, can be used for air conditioning valves, up to traction motors, which is about 80 to 90% of our business. And our customers are normally tier ones and car manufacturers from all over the world, some of them sitting in the audience. I talked about requirements from e-mobility. So e-mobility is somehow different than industrial applications. And this also leads to designs that we cannot see in industrial electric motors. Why is that? One of the reasons is the highly automated production. When we are doing 500,000 pieces of electric motors, or even more than 1 million per year, you have to look at the design. You have to automatically manufacture the design. It's not allowed that you just throw away like 5 or 10% of the electric motors, like it's sometimes done in industry, because they have lower volume numbers. So this is, for instance, one of the main reasons for the hairpin winding that you see nowadays. It's not only about efficiency, it's also about manufacturability. On the other hand, there are the conventional things like the package mass restrictions. Of course, everything has to be low cost. This is a very high demand, especially from the Asian market, but also in Germany. We are facing now very high speeds in electric motor. So not all of our customers are approaching this, but there are many of them that are trying to reduce the size of the electric motor. And one of the ways is to increase the highest speed of the electric motor. The highest application we have seen now in mass production is about 27,000 RPM. This is, I would say, crazy for a motor design engineer, because at this high speed, which means also high stator frequency, a lot of things come into mind which are difficult to solve, difficult to simulate, and lead to a lot of compromises in design. Of course, they're also switching automatically somehow. Okay, and if we address the efficiency, it's not about looking the efficiency map like everybody does and looking at the best point, which is something like 97%. We are talking about cycle efficiency. We have a driving cycle. Sometimes it's maybe not so realistic, but it's there. And everything that goes on with optimization on electric motors regarding efficiency is meant to be targeted on this driving efficiency. There are several different cycles. The problem is that the driving cycle always is located on the lower part of the torque. That means a lot of things, auxiliary losses in the magnets, bearing losses, mechanical things like air dragging losses, especially with high speed, are very important. Not only the copper losses. So everything has to be looked at up here. And last but not least is the functional safety operation, which is my topic today. So even if it's maybe not the main task of the machine designer, we have to look at the failure reaction, especially of the three-phase short circuit, since this is the main so-called safe state of the electric machine, at least in Europe. I know there are different approaches in Japan. Yeah, and this is really putting a lot of different things to the electric motor. If we look at the different machine types, maybe just a short overview. There are several types. This is a very relatively simple approach here. I'm talking only about the permanent magnet machine, since right now this is the dominating technology. Everything I'm addressing today is also related to other machine types, but for an induction motor maybe, it's much more difficult to simulate those things than it is with a PSM machine. Nevertheless, it has been done as well. But everything today is focused on the PSM machine. Next. Yeah, I said there are many requirements. none of them is really alone. So everything that is existing on electric motor that has to be addressed in the design is connected to each other. So when you are designing for efficiency, you are touching cost. You're also touching safety, and you are touching NVH. So you cannot just look at one of those targets and optimize alone. You always have connected targets which you have to look at the same time. Of course, this depends a bit on the application. For a traction motor, it's maybe the worst thing here because you need to optimize everything. For smaller motors like oil pumps or anything else, it's maybe a bit easier. If I talk about failures in electric machines, there are separate causes of these failures, which can be mechanical failures, like a disruption of the AC cable, some broken connector, or even a disrupted winding. There could be insulation failure arising from partial discharge, from wrong manufacturing, or just statistical errors, maybe, because an enamel wire is not always perfect. There is some failures per 10 meters that has to be defined. And just by coincidence, if those areas are close to each other, there can be an insulation failure. This is normal. And another big issue is software failures. To tell you the truth, in reality, this is 99% of the failures, because you know, software is complex. Software has to address a lot of things. So it's almost impossible to do a software without failures, without errors. And those errors, which are mainly influencing the inverter, have also influence on the electric machine, and we have to address that somehow. And there are the hardware failures coming from the inverter, which is mainly IGBT or MOSFET failure, just by high current or durability or some overvoltage. But also gate drivers or EMC filters can be a cause of those errors. And not all of them, but some of these failures would require that you do something, because there's a real driver sitting in the car. You cannot just say, okay, stop operating, and the driver has to do something. So especially if you go to highly autonomous driving, where the driver is maybe asleep or reading in a book, there's nothing he can do, at least not fast. You have to do something and really investigate a lot about those failure reactions. And one of the things that you normally address with those failure reactions is the so-called safe state. What does it mean? Safe state means you have to reduce the energy potential in the system, which could be dangerous. With the battery, it's not possible. It's always there, of course. But even the rotating electric machine has some energy potential due to the inductance, the energy, the rotating energy. And you have to reduce those energy as fast as possible, or at least disrupt it in a way that it cannot influence the driver or lead to any dangerous situation. With the IPM machine, you have the special problem that whenever you have a rotating machine, you have an inherent induced voltage. This is not the same on induction motor and also not on a reluctance machine. And this problem can be solved by just using a mechanical clutch. Then you disconnect the clutch, which is also not so easy, because when you have a high torque on the clutch, it cannot be opened so easily. But in most cars, we don't want to have a clutch. It costs money, it needs space, and nobody wants that. So you have to find some other way to do this. You could use a discontactor on the AC line, but you could imagine if you're running 800 amps, it would be quite a big device to really mechanically disconnect the AC lines. And the reliability on those pitches needs also to be very high. So it's not really practical to do that. In industry, that's the approach they take. With EV, it's not possible. So on the other hand, if you just switch off the IGBTs or MOSFETs, you are ending up having an uncontrolled rectifier operation, which is here on the right side. You don't have only IGBTs, you normally have parallel diodes in there for certain reasons. And when you open the IGBT, the current is flowing through the diodes directly in the battery. And if the battery is already fully charged, this can lead to a dangerous situation in the car. So this is normally not so easy to do that. So the other approach that is normally being taken in Europe is the so-called active short circuit. So you are putting a three-phase short circuit on the lower or upper part of the IGBTs, and then you at least have energetically disconnected the motor from not from the inverter, but from the battery. The disadvantage is in the motor, there's still a current running, and the cooling system needs to be operational, because otherwise the motor gets too hot. And also the inverter has to survive those current. A lot of people that are designing these motors are looking in the stationary behavior of this kind of stuff. That means you're looking what happens if you have this current for a long time. Long time in this case means a second or more. This is quite easy. And you can do this also with analytical formulas. So the curve that comes out from stationary behavior, in this case also calculated by our JMAC, is something that we normally need to provide to our customers. On the left curve, you see the open circuit, which means all IGBTs open, and the short circuit behavior. And one possible approach is in low speed region, you use open circuit, where the induced voltage is low enough so that there's no current flowing to the battery. And in the high speed region, you use the active short circuit. Of course, you need a speed information for that. So regarding the safe state demands, you at least need a sensor that is functioning. This sometimes leads to a situation where you need a second speed sensor, redundancy in the speed sensor to make this switching possible. On the other hand, you see that there is still current flowing, in the three-phase short circuit, as shown on the left curve, and there is of course some torque involved as well. So this is also something that needs to be considered. The torque shouldn't lead to any dangerous situation on the car. You might drive on slippery roads, some icy road. So anything, the uncontrolled torque is dangerous. And the current, as I said before, is heating up the machine and maybe also endangering the inverter. So every of these values needs to be known here, needs to be simulated. How do we approach that with JMAC? There are several possible approaches or simulation techniques you can do. You can use the circuit editor blocks to fully model the control loop, like in Simulink, everything graphically controlled. This is an approach for easy control circuits, can be done. Although in my opinion, there are still a few blocks missing in circuit editor to do this. The better approach to use circuit editor combined with Python code blocks, which is a quite strong feature in JMAC, because you don't need any big Python environment. You just put in the block, put in your Python code, and don't have to care about any surrounding compiler or whatever. This is working quite well. One advice would be don't use the inbuilt Python version, which is 2.8 actually. You need a newer one. I don't know which one, but we use 3.8 actually, and no problem with that. But the 2.8 can lead to problems, the inbuilt one. So you need to update your Python version. You can use a co-simulation. I think there's a good presentation this afternoon about this topic. We have done this in the past as well, not for safety, but for control. Problem here is it's very time consuming. The setup is not so difficult, but due to the two simulation programs, it's also high cost. And this is normally only taken if you need to take really the realistic control. Maybe you have already a sophisticated control system existing in the Simulink from your control guys, and you need to connect this to your electric machine, then you can do that. But regarding the timing constraint, it's not possible to do big variation, parameter variation with that. So yeah, maybe that's not the way to do. And of course, the best way is used to get real test bench values, if you have them, for normal operation, like you have measured the current with the transient recorder and put this kind of current in your JMAC simulation. You can do this just by data table, lookup table. You can also do an FFT and use the FFT spectrum current to put this as an input current on JMAC. This is also possible, but those current normally doesn't exist at the beginning. You don't have a test bench. So you are purely relying on simulation. So really the red outlined approach here is, in my opinion, the best one. Just one reminder, if you don't want to go too much into EM control theory because you are an e-machine designer and have no relation to control, there is a lot of stuff on the internet you can take over for also Python code, so you don't need to do everything by yourself. Just one example is mentioned here, which is called Modulator. It has a lot of control stuff already inside, which you just take over and use that. So this is an example of a transient simulation, which we normally do for our customers. You see here from normal operation, the switching of the three-phase short circuit current and the switching off of a certain period. So if the failure is away, the software failure, and you don't need the active short circuit anymore, you also have to look what happenings if I switch back to normal operation, or if I switch back to open circuit. As I explained, this can also be a strategy. So it's not only the switching on, also the switching off that needs to be looked at. And you see here the current and also the torque reaction, especially the current is has a peak on the first First overshoot, which can easily destroy the inverter. But if you think that's already the worst case, it's not. The real situation is somehow different. In the real situation, you don't recognize your failure if it occurs. You need some reaction time. The software is really calculating low pass filtering, and only after a certain amount of time, you are aware that there's something happening in the system. And this period is really critical. You have to look at the system behavior also in this period. And the longer the duration is, if you switch then to active short circuit, there's really a strong overshoot. So this situation somehow depends on the kind of failure you have and also on the failure reaction strategy. So you need at this simulation stage to know a lot about how the control system could react to those failures, or to have at least a slight idea of what is going on in the system here. So, and it's also depending on the detection time. It can be as high as 250 milliseconds, which is the value of a real requirement catalog for a resolver failure, for instance, which is not so easy to detect. Of course, if you had disconnected phase line, this could be easier, or the reaction time is much shorter than that. But still, you need to simulate that. And then you have the response time if you switch until the system reacts. Of course, this can also be simulated. This is just an example of a simulation approach we normally take. You have the conventional DQ current controller. In this case, I have a third harmonic injection for certain reasons. I know I don't need this anymore from version 22. In this case, I have done this to make the current more sinusoidal. And there's a failure switching matrix at the end where you're introducing open circuit, short circuit. And of course, this could be more complicated than this. You can, for instance, use a switch across an inductance or a part of the inductance, because there are also interwinding short circuits that you might need to simulate. The failure situation that your functional safety guy will tell you is normally not the one that is most probable. The most probable one is the one phase open. So you just disconnection of one phase due to mechanical things or connector problems, but also a short circuit in the inner windings. So directly in the slot, for instance, from turn to turn, or just several turns crossed, which lead to overheating because you have a short circuit indirectly in the tooth. This can be quite complicated, but this really happens. So you have to know what's going on before you build the machine. Yeah, next slide. This is a result of this particular simulation here. Maybe I have to explain it a bit. On the right side, you see the control value that I put to the system. The red signal is the set value for the Q-axis current. So I put a ramp at the beginning. This makes it easier for JMake to not have any overshoot at the beginning. This is also realistic, and this is how it's done in reality. And then you have the current. The set current is a blue curve, which is basically following the red one. And then at a time about 7 milliseconds, there's a disruption of one phase. And the control system doesn't know that this is going to happen. So it's still trying to control the current. And what is happening here is really high current, as you see on the left picture. Yeah, you really have this high current. The short circuit is not right, it's open circuit. And this can easily destroy the inverter, as you can imagine. This is 1,500 amps in this case. And this is normally a current which is an inverter will not survive. Even if it's only for one period, it will destroy the IGBT. And this happens in the reality and has happened in the past already, because people haven't looked at those failure scenarios and they learn from experiments, which is the most expensive way, but maybe also a good one. Yeah. Yeah, no, this is a simulation with a delayed current. So at the beginning, you have a disruption of the phase, the red one, and then you see the three-phase short circuit at the end. And the current is increasing a lot, even in this short period, which is about 13 milliseconds only. The failure reaction normally takes much more time than this. And you don't need the three-phase short circuit anymore because the inverter is already destroyed in this case. And those complicated simulation needs to be simulated with JMake to really get a picture here of what's going on, and maybe to adapt your safety strategy accordingly. That means you have to redesign the machine, make the magnets weaker, which you don't want because of efficiency issue, but you have no chance. So the normal machines that we are designing don't have the strongest EMF, the strongest magnetic induction in the air gap, because from safety point of view, it's not possible to do that. Now I come to the conclusion. So generally, electric machines in EV are very reliable. So this is maybe a picture that is only affecting a certain amount of electric motors, but it's especially targeted to high performance cars with more than 700 amps phase current, 800 volts DC voltage, and so on. The machine designer needs to consider the side effects and not only focusing on efficiency and cost. And also common mode failures and issues. So if something happens and as a consequence something else happens, this is called common mode failure. And this is are not two separated failure. This has to be considered as well. Yeah, the inverter battery and also the gear train, of course, is also affected. If you have a high torque peak, this might also destroy the shaft on the gear train or something in the inverter. And the investigation needs to cover the stationary failure as well as the transient failure. And transient failure is more difficult. It takes more simulation time and variation. Sometimes it's difficult due to timing constraints. Now, the transient failure can lead to very high currents and of course can also damage the magnets, which is another issue. So whenever you have those high currents, you might look only at the inverter IGBT, but after those failures, the magnets lose their remanence and you might have already 10 or 20% lower remanence, which is also not allowed. So those kind of simulations are normally also done for demagnetization. And the question is, what is the worst case for demagnetization? Anybody knows? I don't. Normally, we are looking at three-phase short circuit, transient, and that's it. But as I said, that's not the worst case. Worst case is different. PWM switching might need to be involved. We haven't done that so far due to simulation time, but I think in future simulations, we also need to consider PWM here. And the real failure sequences are probably much more complicated than I have shown here. And at the end, we also might need a co-simulation with the mechanical system, which I didn't address here. So because there's thermal inertia, there's changing of the speed from braking, which is also affecting the failure sequence. If the speed changes quite fast and the resolver is stuck, so he doesn't measure any speed anymore, you are running at the wrong frequency. I don't know what's happening in the machine then. Interesting simulation. And there's much more than that. So this is just the beginning. I think we need to go much more in those sequential failure simulation and look a bit more on the system level to understand what's going on here. It's maybe also a task for some professors at the university to look a bit more theoretically in the system and say, what is the worst case here? So thank you for your listening, and I'm ready for questions.
Bernd, thank you very much for this nice presentation. Are there any questions you have regarding this presentation or to Bernd?
Thank you so much. Very nice presentation, as always. So my question is not really technical. I think that issue is very, very important for advanced application machine technology. The question is that who should take care those issues, machine designers or control or electrical engineers? Because like such failure state cause many problems, both sides, circuit and machine. And then we need to take care about some detection time, those things. And I mean, I'm wondering who should take care of those issues, which part?
Thank you for this very interesting question. This is basically putting the focus on the most difficult issue, because nowadays it's not really established that everybody is talking to each other, especially at an early stage where the control engineer doesn't really know its control system. And the functional safety guy has some rough idea, but has no idea how an electric machine works. So the solution is everybody's sitting on one table and discussing how a potential solution can look like. At least that's how we do it. And it's not really established right now. But the only way is everybody talks to each other, and simulation needs to be taken by the FEM designer, not by the control engineer. One approach could be that we are doing an RT model, putting that to the control engineer and they can simulate. But I don't think the RT model is accurate enough to cover those failure sequences here.
Okay, I understand it's a bit difficult. Okay, thank you.
Thank you.
Any more questions? Yes.
Thank you for your last presentation. Tianjie Zhou from University of Nottingham. Basically, during the development of PSM, we have realized that the most significant challenge in reducing the permanent magnet usage is basically not in its in achieving its peak performance, but in the design task of reducing the demagnetization issue. And in most cases, we have been asked by our research partners that we need to cover the situation where the short circuit, active short circuit happens with very high peak current transient. And at this kind of challenging operation points, we need to limit the demagnetization ratio to be below, for example, 2%. And I have realized that in your presentation that in low speed region, with very high torque, for example, which typically will increase much higher transient current compared with field weakening region. You've mentioned that we can simply do open circuit arrangement. May I ask if there's any technical challenge in doing this in, for example, when the motor is operating with very high current?
You mind the switching between open and short circuit directly?
Yes, basically by switching from a normal connection to a sudden open circuit connection.
Yeah, you can do some intermediate operation. It depends a bit on the failure case. To optimize the phase angle, for instance, before you switch to short circuit or to open circuit. But yeah, there's no easy answer to that. So right now we have also an increased demagnetization ratio due to that issue here, which is even 4%. But there's not much you can do. Reducing the magnet mass, put the magnet deeper in the iron, use grain boundary diffusion magnets, which everybody's doing now with a lot of problems. This is a dedicated topic maybe for next presentation. It's a nightmare to call it easy. And yeah, no easy answer to this. So, but you look not only to open short circuit and short circuit, also to maybe do some intermediate thing. One approach, for instance, or one idea is to switch very fast between short circuit and open circuit. You find this in literature. If you do this quite fast, you have some like a PWM between open and short circuit, and this can reduce those issues. But I've never met anybody who really tried this in reality, and it needs some research.
Thank you.
One more question?
Abdelak Mikalia from Immotors Company. I have a question about if you have some kind of modelization to simulate the duration, the maximum duration we could have under ASC mode, for a given function point. If do you have some ways to modelize the demagnetization that we could have and the thermal behavior in general for these modes?
For the thermal behavior, there's just conventional thermal modeling, like with normal operation for the three-phase short circuit. For demagnetization, we use the recoil permeability, like it is done in JMAC. So you just do an open circuit at the beginning, then you do short circuit, whatever is reaction on the failure reaction. At the end, you switch again to open circuit, and you see if the voltage has changed. This is also the same way it is done in experiment. So on a test bench, you do the same way. You're looking at the open circuit voltage before and after. This is the easiest way, but there's something like a BH view right now on, if you make a point view in JMAC, you can not only look at the magnetic inductance, but you can also do a BH view, magnetization against magnetic field strength, which also shows you curve line if there is demagnetization or not. So, but to convince our system engineers and my managers, because they are not so much into this electromagnetic stuff, you look at the open circuit voltage because everybody understands that.
Well, thank you very much.
Yeah, you're welcome. Thank you.
One more question from your side?
Thank you, Hirix from JSO. So not question, but comment. We are now moving to the Python 3.8, so we're stopping the old version, so it's fine.
Thank you. You know the issue probably. Yeah.
And the question is, you mentioned about RT, but we also need to care about the demagnetization dynamically. So we need to support dynamic demagnetization in RT, or we need to think about FEA direct link with the control.
For RT, this would really be nice to have that in RT, because then, as Takashi asked, we can shift the problem to our control designers. If we could deliver an RT model, then the control engineer can take care of a lot of failures, which is not the case right now.
But now we just support static characteristics, so we need to think about dynamic behavior of the machines.
Yes.
Okay. Thank you.
You're welcome.
Do we have a fifth question or not?
And thanks again for the audience, and maybe we have time some questions during lunch break or
yeah. Okay. And thank you very much for this presentation. Thank you for the questions and the discussion.